Welcome to Ideas on Tap, presented by the Museum of Natural and Cultural History. My name is Lauren, and I'd like to start this evening by recognizing that the museum and the University of Oregon are located on Kalapuya Ilihi, the traditional indigenous homeland of the Kalapuya people. We recognize and honor all indigenous people who continue to call the Willamette Valley home. If this is your first Ideas on Tap, welcome. If you're one of our regulars, welcome back. I'd like to thank everyone who has joined us this evening for taking a break from checking the news obsessively every 30 seconds, like I know I have been doing since last night. Or maybe you're still checking the news right now, and that's okay too. So it's been a long day, and I'm sure many of you, like me, could use a good cup of coffee right now. So we have a really great talk lined up for you. Although we might not be together in person, we do still want to hear your questions and your comments. If you're joining us on Zoom, you can use the Q&A or the chat box. And if you're on Facebook, you can use the comment box. I'll be collecting your questions across both platforms, and we'll get to as many as we can at the end. As some of you may know, we normally host our Ideas on Tap program at Viking Braga Company's Southtown location. Hello to all of the staff over there, and know that we miss you. I hope that some of you were able to pick up some food or drink to go tonight to give yourself the full Ideas on Tap experience. And I have some great news. Starting next month, you'll be able to enjoy your braggot right out of your very own Ideas on Tap pint glass. We now have them in stock in the museum store, so pick one up today and get ready for next month. At the end of this program, we will be posting a link to a short survey in the comments on both Zoom and Facebook. The link's on the screen, so you don't need to copy it down though. If you could take just a few minutes, it should only take 1 to 2 to fill out, we'd really appreciate it. It'll help us improve future virtual programming, and you'll be entered to win a $25 gift card to Viking Braga. Before we get started, I have just a couple of upcoming programs I'd like to share with you. In just over 2 weeks, on Thursday, November 19th, we'll be hosting a discussion of local concerns about fire danger, forest management, and the role of climate change in the wake of the Holiday Farm fire. The panelists will explore how the revitalization of Indigenous fire science could help transform our relationship with wildfire. Then on Wednesday, December 2nd, we're back for another Ideas on Tap. Join us for a discussion about race and policing and how current policy approaches fail to address the demands of activists and community organizers. I hope to see you there. Finally, if you enjoyed tonight's program, please consider making a secure, tax-deductible donation at the web address listed on the screen. That's giving.uoregon.edu/mnchgift. If you're able, we recommend a $5 donation, or you can make a larger donation now and tune into Ideas on Tap each month, knowing that you've already done your part. Your donation directly supports the museum's educational programming, bringing science and culture adventures to Oregonians of every age and in every corner of the state. Thank you. And with that, it's now my pleasure to introduce our speaker for this evening, Dr. Christopher Hendon. Chris is a professor of chemistry and biochemistry at the University of Oregon. His research interests include energy storage and conversion, and as part of the U of O's Energy and Sustainable Materials Initiative, he is searching for innovative ways to make better batteries and solar cells, as well as solutions for greener manufacturing. He has also applied the same scientific principles to brewing the perfect cup of coffee, and he's here to share the science and some tips with us tonight. Welcome, Chris.
Oh, thank you very much. I didn't realize until just a moment ago that this was usually held in person at Viking Braga. So I feel like somehow we got shortchanged in this one. We're going to have to do this again at some point. I prepared a presentation for you, and this may or may not be longer than the average one that you have received before for the Ideas on Tap talks, in part because coffee is one of these topics that we all know just enough about to perhaps have a different foundational knowledge that we need to build off of. And so I'm going to start from the very beginning and build up. So usually I like to tell you about where I'm from. My grandfather actually notified me a while back and told me that I needed to get my DNA sequenced. And after we moved away from the concern of why that might be, I did actually learn, that, quite interestingly, that my oldest ancestor, my Adam, if you like, 60,000 years ago was from sort of roughly Kenya, Ethiopia, which incidentally happens to be one of the birthplaces of coffee alongside Yemen. So I suppose my family at least, has been working in coffee for quite some time. But actually, despite my American accent, I'm actually from Melbourne, Australia. And I did my undergraduate there, and then I performed my PhD, or received my PhD, at the University of Bath in the UK. And Bath is a city that's founded in the year 3. Some of you may have visited this lovely place. It's named Bath, of course, because the Romans settled here, noting that there was a natural hot spring. The Romans at the time thought that the water had therapeutic properties, and they used to drink and bathe in it. Now today you can still go and visit this living museum if you like. You can't bathe in the water, although people periodically try to get in there. But we'll revisit the water, because this is, water is one of the key things in coffee brewing. So shortly after my PhD, I moved to Boston, New England as opposed to Old England, and spent 2 years at MIT, where I was split between the chemistry department and the chemical engineering department. And then after my time at MIT, I started my assistant professorship here on the tenure track, and I'm now a 4th-year tenure track professor here at the University of Oregon. Now, basically, I wouldn't be doing this job. I wouldn't be able to pursue both the material science and coffee-related topics if it weren't for my wonderful research group. So I first and most importantly have to acknowledge that these are the students that really do all the hard work in my group. The top students there are my graduate students. And then the bottom students are actually one of the wonderful things about Oregon is we get these excellent undergraduates that are interested in doing research. And so we all work together, and we work on topics that range from looking at materials that take light and turn it into electricity, all the way to looking at how we can better brew a cup of coffee. Now, I have to tell you a little bit about my actual job. So if you were to take a handful of dirt from Earth's crust, you would find that, you'd get per million silicon atoms, you'd find roughly, very roughly, this elemental abundance. So, you might find a little bit more oxygen in your hand than silicon. You wouldn't find very much platinum, okay? Yet, the industrial processes that people rely on, so for example, the catalytic converter in your car, the types of transformations that turn small molecules into plastics, these things are typically performed with these rare and difficult to find elements like rhodium, iridium, and platinum. Yet we can still do these types of chemical transformations with more earth abundant materials. Nature does it all the time. They use enzymes. And so basically what rhodium is used for in industry, nature uses an enzyme that has 2 nickel metal ions in there. And for what we might use platinum for in industry, nature does that with an iron nickel complex. And so basically, my group is interested in using these earth abundant metals to do chemistry that is typically reserved for the sort of more rare metals. And I want to give you one example. We work with these class of materials that basically are made from organic components and have inorganic regions as well. And because of that, we call them metal organic frameworks, or MOFs. And in this particular MOF that we studied, it has a nickel center. And this nickel center is capable of taking 2 ethylenes and coupling them together to form 1 butene. Now, 1 butene is a very important chemical feedstock in making polymers, and this process is quite energy intensive. But using this MOF, we found it actually has lowered that energy requirement and also made this 1 butene more selectively. So overall, we've been able to do the type of chemical transformation we aim to do with something that falls above that line of ubiquity in the dirt, if you like. And so this is what I'm employed to do. But I think actually Oregon might have got a little bit more than they were expecting from me, because I also have this other life in coffee. And with that, I want to note that there may be topics that I don't get to cover today that you might want to hear a little more about. So I'm going to link you here to 4 different talks that I've given that are recorded, and you can find these simply by Googling a comprehensive talk, for example, on water chemistry and how it impacts the flavor of coffee is the bottom one, and so forth. Also, feel free to send me an email afterwards if we don't have enough time during questions. I also want to point the more interested listener today towards a repository of papers that I curate on my personal website. These are peer-reviewed articles written by not only myself, mostly other people And they are vaguely related to coffee, but I also just think they're quite interesting. So for example, you can find papers from 1990 JAG Food Chem on the Rio defect, which is a defect that you find often in coffee. But you can also find things like, for example, the misuse of the word sour when you mean bitter. And this is more of a sensory science paper. If there's a paper that you come across in your journeys that you don't have access to, also email me. I'd love to read it, write a short synopsis of it, and put it on my website. So my coffee journey begins walking into a cafe in Bath and being greeted with this board. This board is more than just a menu, it's a map. Basically, it tells me if I'm going to order an espresso shot from this particular coffee, this Brazil, Paseo, the Ruby variety, and natural, I might expect then that it tastes like fruitcake, brandy, and toasted seeds. I don't yet know why it tastes like fruitcake. Is it because it's from Brazil, or is it because it's the Ruby variety, and so forth? But I also note then that when I take this espresso and I add milk to it to make a cappuccino or a flat white or a latte, that the flavors change. And now I might expect dark toffee, cocoa, custard, and Brazil nuts. And so for every coffee, one could write out the so-called flavor notes that you would expect in different formats. The ones on the left here are espresso-based. The ones on the right are filter-based. And so really what I'm looking at now is quite a complicated menu in the sense that there's lots of flavors, and it's really teaching me that there's a lot to explore in coffee. Now, some of those flavors may seem appealing to you, and some of them may seem sort of off-putting. And it's really not about, this whole topic is not about telling you what's the best coffee. And it's not, I'm not trying to tell you how to change what you do or how to brew better coffee. Let me repackage the point of my work in coffee is that the coffee industry is trying to produce a product that achieves some sort of expectation for the consumer. So for example, if I told you that this cup of coffee would taste of lemon peel, bergamot, and watermelon, and you received it, and occasionally it would taste like salmiakki, which is a salted Finnish licorice, dirt, and Brussels sprouts, then there might be an issue there because obviously now you might value the product differently. Perhaps the reason for that might be the barista, because that's the easiest variable to point to. But actually, hopefully by the end of this talk, I'll convince you that it is more than likely the quality of the green. In other words, the natural product, the coffee bean itself, that was variable. And then in equal contributions giving rise to that variation in the cup are the roast profile, who roasted it, how they roasted it, and then the water chemistry, because the water chemistry, of course, can change the flavor that you might perceive in that cup. And at the least important aspect is the equipment, which may come as a surprise because the equipment, of course, is the most romantic of the bunch, because that's what we as end users interact with. Now, the reason I only give it a 10% rating here in terms of importance in determining cup quality is because when we buy coffees in the first place, we actually don't really use any brew equipment at all. In fact, coffee is graded on the so-called cupping table, where we take 5 samples of the same coffee, we grind it, we put it in a cup, and we pour hot water on it and taste it with a spoon over a series, let's say 15 minutes. And so hopefully then you can see that this is basically no brew method whatsoever. This is analogous to how traditional Ethiopian coffee was brewed, something like the Turkish brew method, except for it's not, constantly boiling. And basically what you have here is no equipment whatsoever. Now, what you're looking for when you cup coffee is you have a score sheet that for a standardized taster, somebody who has been trained to identify what a 6 means on this spectrum of, for example, flavor, and a 10. And if you're calibrated, then you are able to assign an absolute score to this particular coffee. Now you'll note that high scores rank, above outstanding, and the worst score on this is good. So I quite like working in the coffee industry already, because even the worst cup of coffee you've ever had in your life is still good. But more importantly than that is that this panel acidity, right? And so I highlight it for you because acidity is one of these things that humans do like. But acidity, sourness, tartness, these are all sort of operating in that same regime, that same realm of flavor. But positive acidity, something you enjoy, actually also alters the way that we perceive sweetness. And so you can see sweetness is over here. And then overall, if a cup is lacking acidity, you might not enjoy it as much. And so the acidity panel is really a multiplier. Now, if you score 80 or above out of 100 on this score sheet, this coffee is graded as a specialty coffee and fetches a higher price for the farmer. And if you score below 80, that is called a commodity grade coffee, and that of course is not that's worth far less money. And so hopefully now you can see that we're just painting the picture that coffee comes in, a low quality coffee that you enjoy doesn't mean that you're a Philistine. It simply means that you may value one of these panels less, and that's good for you because it's cheaper, right? But I did mention that the equipment is the least important thing, and you don't need to spend much money to achieve high quality unless you're NASA. And so when I visited the University of Pittsburgh, they actually showed me a reproduction of the NASA Space Cup, which allows astronauts to consume coffee in zero gravity. This, of course, was a very expensive cup to design. And here you can see astronaut Lindgren sipping coffee in space in the International Space Station. The way it works is a spherical amount of coffee goes into this aperture here. And because of the capillary effect, the coffee will wet the inside of the vessel along this ridge. And once it pools at the lip here, you can see the human will then be able to suck on that lip, and the liquid will flow from the cup into the mouth, and you can drink coffee in zero gravity. Of course, most of us won't get to experience drinking coffee in zero gravity, and so we'll just come back down to earth and start this journey to understanding the coffee science with the plant. Coffee is extremely valuable. So the most recent data I have was the 2015 market analysis, which put coffee at about 1.3% of the US GDP. Within the United States, coffee is primarily consumed as drip coffee or filter coffee, which is 1.2 to 1.5% by weight coffee. So in other words, if you had 100 milliliters of coffee in your hand, about 1.2 to 1.5 grams of that liquid would actually be coffee. The rest would be water. In Europe, espresso dominates, okay? So that's a much more concentrated beverage. Let's just very roughly approximate that drip coffee is 10 times less concentrated as espresso, okay? But in countries like Burundi and other coffee producing countries, the coffee production and just generally the contribution to GDP is tremendous. So basically 90% of the people in Burundi work in the coffee industry. That's everything from picking to packaging to shipping. And it contributes about 25% of their GDP. So a bad year in consumption in the American market is like catastrophic in Burundi. It's not only Burundi, of course. Burundi is just one of many African countries that produce coffee. And there's also, of course, South American, Central American, and some Asian countries are now producing high quality coffees. And within this so-called bean belt, the key thing that you need to grow coffee is low CO2 concentrations in the atmosphere, relatively stable temperatures. And so the way you achieve both of these things is to grow coffee around the equator on the tops of mountains. And the reason you want low CO2 is because the plant is converting CO2 into sugar via photosynthesis. And if you think about what the coffee bean actually is, it's the seed inside the grape rather than the grape itself. So you want the plant to reach maturity, so the seed is what we get and not too much fruit, right? And so even within those coffee producing regions, there's two different types of coffee. There's coffee Arabica and coffee Robusta. And basically Arabica grows at high altitude, but it also is susceptible to pests because it doesn't produce nearly as much caffeine as Robusta. So caffeine itself is actually a small organic molecule that, of course, we're all familiar with, but it's actually toxic. And periodically you hear about humans drinking far too much coffee and dying. Well, if you're a little bug and you consume too much caffeine, then they also die. And so it's sort of a natural repellent for pests. But while these two products look the same, Robusta and Arabica, they're actually so genetically dissimilar. It's just remarkable they even roughly taste the same. Arabica has twice the number of chromosomes as Robusta. Now, of course, chromosomes are not an indication of complexity, so there's not really a relationship there, but simply pointing that they are different. Now, as I mentioned before, coffee begins its life as a fruit. And so on the left-hand side, you can see a coffee cherry. It looks roughly like the size of a cranberry. And if you crack it in half, you'll find a book-matched pair of seeds. And if you find only one seed, that's called a pea-berry defect, and indeed was the origin of the name Pea Berry's coffee. The defect doesn't augment the flavor necessarily. It's just the observation there's only one. Now, once you remove sort of the fruit and then this outer parchment, you end up with the seed, and this green seed is what we call green coffee. And this thing is what gets put into the roaster, okay? But you have to get from the left to the right somehow. And so if nature had its way, the plant would fruit, the fruit would then fall to the ground, it would dry up like a raisin. The raisin may or may not be removed somehow, and you'd end up with the seed, right? And so when humans intervene, we call that the natural process. We simply pick the cherries and then we dry them out and make a raisin, then remove the raisin and we get the seed. The pulp natural process is where you first hit these cherries and remove the skin, but you leave some of the fruity mucilage stuck to the outside and then you dry that. And then finally, the wash process is where you use water to just wash off all the fruit and the skin and you end up with the seed right here. Now, much the same as chocolate, you basically take or cacao, as I should say, but the seed then goes into a fermentation process for, I don't know, approximately 24 hours. And so basically what that's doing is chewing up any residual sugar on the outside, but also, imparting some flavors. And that's an area of active research. So here's a photo of naturally processed coffee. This one right here, the bright red one, is freshly picked cherries that are drying in the sun. The darker red is drying in the sun over a longer period of time. And then behind it, you can see washed coffees drying out on those raised beds. There is a lot of interesting chemistry that occurs when you process a coffee naturally. But one of the things we certainly know is that naturally processed coffees that have had either a fungal or bacterial problem fluoresce. And so actually coffee farmers will shine black lights on their coffee and then sort the ones that are fluorescing out as they taste defective. We still don't yet know all of the details as to why these things fluoresce or how to prevent it, other than trying to prevent spoilage of fruit drying in the sun as we do with raisins. Okay, so it's an active area of research. And so at this point, you might then say, well, what is the best coffee in the world? And some of you may have heard of Kopi Luwak or civet coffee. This right here is a poo. And these are coffee cherries that have been consumed by a small animal. The animals use the fruit as energy for its body, and therefore it's somewhat like the wash process. And then, of course, the remaining seeds go into its intestine, where it's basically simulating the fermentation process, and out comes this. This is then washed and is prepared for roasting. Now, is this the best coffee in the world? No. In fact, I've never seen once a civet coffee ever score above 80 points on a score sheet, indicating that actually, not only is it not the best, it's one of the worst. And in fact, there is no real best, because the best is defined as this, whatever scores high on the score sheet that particular year. But I can tell you that the ones that score low are typically Brazil, Sumatra, Vietnam, and Hawaii. And the reason is they have low perceived acidity, which means they score low on that score sheet. The Panamanian geishas always tend to score high, either natural or washed. And the reason for that is that they have all the lovely fruity character and acids that we tend to enjoy in coffees. I also want to point out that the word geisha here has nothing to do with the Japanese woman. Instead, it is related to the original producing region in Ethiopia, Gesha, and perhaps the addition of the I as an appropriation that over time. So at this point, we've got green coffee and we need to turn it brown, independent of whether it was a natural or a washed or a pulp natural, right? And so simply put, you start roasting, you heat it up, and at some point you'll audibly hear a crack. It occurs around 9 minutes or around 205 Celsius. And this crack is the release of carbon dioxide and gaseous water. And then as you continue on, it starts to brown and darken, the crack ends. And then at full city plus, you start to hear another crack, so second crack. And once you go past second crack, you're getting into really, really toasted coffee. And so most high-end coffees are roasted to around 10 to 12 minutes, and then sort of the lower quality coffees are roasted beyond that to hide any of the negative flavors. Now, should you like more developed coffees, more roasted coffees, that's absolutely fine. You can also take a lovely high quality coffee and roast it darker. It'll still taste wonderful. From a scientific perspective, roasting is a little more nuanced, okay? So think of a heated up cement mixer. You're measuring the air temperature on the inside of the cement mixer, and you drop in room temperature coffee. So the heat will then transfer into the coffee, and we call that the soak. And then as you start to heat up the air again, the coffee, the temperature in the roaster increases and the coffee starts to roast. You're driving off water for the first part, and coffee contains a little water. And then after first crack, we call that development. So that's the development time. And that's basically where all the action happens. So the longer you develop, the darker the roast, okay? It's not the higher the temperature, right? So indeed the temperature goes up, but it's not like you're cooking it, really rapidly. It's just increasing roast time. Okay, that is one way to roast coffee. But if you were in the chemistry laboratory, you might think, well, I could use that coffee waste for something else. And so in a recent paper in 2017, the authors showed that this coffee waste could then be re-roasted in the presence of zinc chloride under an argon atmosphere to a very high temperature. And the resultant product is this material called N-doped carbon. Now, N-doped carbon is useful because it conducts electricity and it does the same sort of transformations as platinum. And so if you think back to my original motivation in my research group, this is exactly what I'm interested in, using earth abundant materials to do simulated reactions like platinum does. And so I thought this is good. Okay, so what's in roasted coffee? A lot. So here is about a quarter of what is detected over the years from just putting sampling the aroma coming off of the coffee, let alone what's inside the liquid itself. And I don't think it's overly useful to talk about molecules specifically, but rather to talk more holistically about sort of flavors and effects. Now, of course, we all care about caffeine, right? So we do know a little bit about caffeine. We know that the plant produces it. It's not produced in the roast. And so a science paper demonstrated that in 2014. But we also know that caffeine melts at 235 Celsius and boils at 178 Celsius. So in other words, during the roast process, you could really be destroying it. It could be leaving the bean. But at the same time, you're creating more accessibility to get to it when you try and brew it. So we have this tipping point. We're destroying it with the roast, but we're gaining access to it. And so it turns out then that the roast debris doesn't really change the caffeine content. But what does change the caffeine content is how you brew it. So if you just took a single shot of espresso, you get about 75 milligrams per espresso, of caffeine. And if you brewed a cup of coffee with the same beans, you end up with 164 grams of caffeine, 64 milligrams, of caffeine. And now, sure, brew method changes the concentrations, but the short version of this is that the bigger the cup of coffee and the longer it took to brew it, the more caffeine you get. But here's really what we care about. And a standardized way for me to communicate to you the flavors that we might perceive in coffee. And so there is a reference for each one of these flavors. And at the University of Oregon, I actually teach a class where we go around and standardize our taste. The other day we did sweet aromatics, was a fun one. And we've done a peach as well. And basically what you do is you can look up in World Coffee Research's sensory lexicon, the reference flavors for peach. You then taste this, and that now you know what the definition of peach is according to this wheel, so that when you taste it in coffee, you say peach, I say peach, we all say the same thing. And this is just simply a language. It's a tool. It's not gospel. It's not supposed to say that if you don't taste peach, but someone else does, that you're wrong. But we don't have access to those flavors yet, right? The roast generated them, but we now need to pour water on the coffee somehow. So before we do any of that, we need to grind it. And so we start out with whole beans and we put it through a grinder, and inevitably we get to something coarse and then medium. And then if you're brewing espresso or something like that, you go even finer. Now, instead of showing you pictures, the way that we would do this in the lab to measure the size of the grind is to, assume that you've ground the coffee with some grinder. We then put it into a laser diffraction device, and the little tiny particles pass by a light bulb. And you can think of this diffraction as basically the size of the shadow it casts is inversely proportional to the size of the particle. So a big shadow means a little particle, right? And there's another way of quantifying size. You could use a scanning electron microscope, and this is pretty nice. This is one big piece of coffee in the middle and a whole bunch of little dust pieces all around it. And these little holes that you see in there are sort of the remainder of the cell walls that were in the coffee in the first place, but then were roasted. If you zoom in, you can see these more obscure shaped objects, and they're sort of small. They're on the order of, let's say 10 to 50 micrometers across. But they're not really spherical. And so basically when you try and quantify how big coffee particles are, it's nice to use an easy object like a sphere or a cube or something. And so really we're asking the question of how big the sea urchin is, right? And is it this big, or this big? Well, of course the sea urchin is this big. That's the space that it takes up. But our light diffraction method measures this big, which means that we're going to overestimate the volume contained within the particle and underestimate the surface area because all the faceting is missing. But it turns out then that actually the spherical approximation works pretty well for those really small, dense pieces. So if your coffee grounds are really small and dense, then the spherical approximation seems to work. So first thing we got to do is make sure they don't have holes in them. And I showed you that previously there's these big cellular size holes in there. Well, if you think back to the type of materials that I work with in my lab, these metal organic frameworks, these things have lots of tiny little holes in them the size of atoms. And so a moth might be able to absorb something like 1 milliliter, this axis is in milliliters per gram of nitrogen absorbed. And so this material can absorb 1 liter, basically 1 liter of nitrogen gas per gram, which is remarkable. Coffee, on the other hand, is not porous, right? It doesn't have these tiny little holes in it. So it can only absorb about 7 milliliters per gram. This is the expectation for dense materials. So then if I grind the coffee and use the laser diffraction method, I'm hoping to see particles on the size order of around 20 micron. Indeed, if you count them, that's exactly what you see. Most of the coffee particles are small. But if you normalize by surface area, those big ones are a lot bigger. And so that spherical approximation then gives us about 15 to 25% of the surface area coming from really big pieces. And then if you normalize by volume, it shouldn't really surprise you that if I held some coffee grounds, the place that was occupied by big pieces would be, occupying a lot of volume. And so the big pieces take up a lot of space. The little ones take up a little less space. Now, how we can understand this grind profile is that you start with a big bean and then you fracture it. And then when the pieces are sufficiently small to exit the grind chamber, they give rise to this initial peak here. And then every time you break the coffee, you make dust, and that gives rise to this hip. So the more times you break the coffee, the more dust you make. And the more times you break the coffee, the smaller the big pieces. So basically, at a coarse grind setting, you have not very many little pieces and a lot of big pieces. And as you make big pieces smaller, the little pieces increase in population. And this observation that I made about coffee was also made for explosive volcanic rock. So when a volcano erupts, the first rock shoots up in the sky is, the same amorphous material of, all sorts of rock, and it shatters in this same fracturing pattern. But you'll note that the small pieces don't change size. They just go up or down in population. So how do you change the small pieces size? And the answer is with temperature. So at room temperature, you have this black line here, but as you cool the coffee down to freezer temperature, you get a more homogeneous Gaussian-like distribution. And you continue to cool and you get to dry ice temperature, it becomes even more skewed Gaussian-like, very, very regular. And then continue down to liquid nitrogen, you get even smaller and more regular again. And so overall, cooling coffee really changes the way that the coffee is fracturing in the grinder. And we can understand this from a material science perspective, that at low temperature, all of these atoms are not really moving. So if I were to crack this material, the crack would propagate cleanly between these atoms. But at high temperature, the atoms are all sort of disordered. And so if I try and crack this thing and get to the other side, that crack will meander. It won't take necessarily this very obvious path over here. As that gives rise at higher temperatures to sort of a more broad spread of particle sizes and often increasing in size. So that's precisely what we see in coffee grinding. The additional benefit of cooling coffee is that about every 10 degrees that you cool something down, basically all the rates of decomposition and spoilage go about half. So if you go from 20 down to minus 20 by storing coffee in your freezer, then you find that coffee's shelf life extends by about 16 times because it's 2 times 2 times 2 times 2. And with that in mind, basically storing coffee in a freezer in an airtight environment prolongs its shelf life of coffee almost indefinitely. Now, some cafes here in Oregon are actually doing this. They're doing not to preserve it, but to gain access to that difference in particle size distribution I mentioned before. So here in Oregon at Proud Mary, you can go and see that all of their coffee is stored in above their grinders in a little mini bar freezer. And then in Australia, at this cafe, Ona Coffee, they have individually dosed coffees that are stored frozen. Okay, so I know I'm pounding a lot of information into you. We got a little bit to go before we get to the end here. So we've got brown coffee that is now ground up. Now we need to add water. So basically, water is a polar molecule. It's got a plus and a minus. So it likes to form these little networks like this. And indeed, the smallest network that water can form is this little hexagon. And that little hexagon on the atomic level is indeed why snowflakes have 6 sides. Okay, but the more important thing here is that water can also point its pluses and minuses towards other species. For example, chloride, Cl minus, likes to dissolve in water because water's pluses on the H's will point towards the Cl minuses. And conversely, if you can dissolve calcium plus because the oxygens point toward it. So, okay, so with that in mind, you can also dissolve things like oils. So this is an octane isomer. And the way that this interacts with water is by water forming cages around it. Now, the cages are really just, disfavored. And so you don't actually find too much oil dissolving in water. And so indeed, that's why they phase separate. You put oil in water, when you make a salad dressing, they separate, right? But you can also dissolve other things like carbon dioxide. Now, We could go into great detail about this, and indeed I point you to that talk that I referenced at the beginning, but let me just summarize this in two quite simple concepts. That from a scientific perspective, we like to think of the positively charged minerals like calcium, magnesium, and to a lesser extent sodium as facilitating extraction of flavor of molecules that have oxygens and nitrogens in them. These molecules, like for example, theaflavin, is one of the flavors responsible for the black tea that you might find in washed Ethiopian coffees. And so we like that. Yet, and the reason that this works is, well, one way of thinking about this anyway, is that the calcium is positively charged and the oxygen bound to this theaflavin molecule is negatively charged, and they stick together. So water containing calcium pulls that flavor out into the water. Another way of thinking about this is that if you have water that contains calcium and all the waters are pointing towards it, then those waters are going to really not want to form cages around these molecules that don't have oxygens. And so, for example, alpha pinene, which is one of the flavors you associate with chamomile tea, basically does not interact very strongly with water whatsoever. And so already at this point, you can see there's a problem. The coffee water is very different to the water you might use to brew tea. They're almost orthogonal to one another. But for every plus, there's a minus. And this minus is really the important thing here, the anion. And so the key one that we worry about in coffee is bicarbonate, because bicarbonate's job is to try and stabilize pH. And if you remember that pH is basically synonymous with acidity, and acidity is on our score sheet. So if bicarbonate's job is to make sure that pH doesn't change, then that means that it's basically making sure that we're not going to taste acids. And so if you have too much bicarbonate in the water, it's then going to wipe out all the acid. But you have too little and the cup's going to taste far too acidic. So I like to think of anions as structuring flavor. So cations are extracting and anions are structuring. To show you the impact of anions, I've gone around this flavor wheel and referenced all of the natural products on the outside of this wheel and found out what compounds give rise to their flavors. And then I've looked at those compounds from a chemical perspective and said, will they interact with bicarbonate? And the ones that do interact with bicarbonate are going to be wiped out. You won't be able to taste them. In fact, they may taste negative to you. They may have a negative flavor. So you can see, I tried to intensify the quote unquote chemical region because it's that's what we call bad, I suppose. But you'd also see that all the acidic panels are being destroyed. And so this is really bad because that means that water that has high carbonate hardness, high in bicarbonate, KH being the German for carbonate, right? It's wiping out the panels we care about. So let's zoom in a little bit. All these lovely panels of all the fruits and acids, you can't taste them in high buffering water, high bicarbonate water. What is left over is floral flavors like chamomile, rose, jasmine, sweet aromatics, brown sugar, and the nuts and spices, okay? And so at the beginning of the talk, I told you that the least valuable coffees are typically Brazil, Sumatra, Vietnam, and Hawaii, because they don't have high perceived acidity in the first place. But actually now I'm going to contend that they're probably the most valuable coffees in the industry, because independent of the water that you brew the coffee with, you are going to be able to taste brown spices, chocolate, sweetness, and flowery notes that may exist in any of these coffees. And so indeed, these low acid coffees actually are really stable coffees in the sense that they transmit flavor independent of the water chemistry. And so without going into much detail, I constructed a graph which helps people understand the relationship between the amount of bicarbonate, which is the flavor constructor, and the amount of calcium and magnesium, which are the flavor extractors. And basically, if you have too little, then the coffee will taste sharp, sour, and empty because you didn't extract very much because you're low on this axis, on the y-axis. And you didn't buffer any of the acids, so you're going to taste all that really sharp acidity. This is the type of water we have coming out of the tap here in Oregon. So if you've ever had a really sour cup of coffee, it's not the barista's fault. It's not the coffee's fault. Indeed, it's actually the water's fault, okay? But if you go into a hard water location, some of you may be tuning in from hard water locations, you often taste heavy, flat, and chalky cups of coffee. And these chalky cups, sometimes people enjoy this because it definitely has body, but it also has bitterness. It's just a very unpleasant cup. And so somewhere in the middle is where we tend to like. And you can brew your own water. Beer brewers have been doing this for as long as I can remember. We can do the same thing for brewing coffee, albeit on a much smaller scale. We're looking at, milligrams per liter. And I'd encourage you, if you are interested in doing this, to reach out to me so that I can give you some good recommendations and so you don't overdo it. Another way of trying out the impact of bicarbonate is just to look at the back of bottled water. Here is a photo I took in Switzerland. You can see they actually tell you in milligrams per liter exactly the concentration of bicarbonate. And so with that, you can actually then try different waters in your kettle and do exactly the same brew method and assess how the impact of these different minerals makes coffee taste different. But let's cast our mind all the way back to Bath, where I did my PhD. The Romans came here because they thought that the water was unique. And if we look at it, it's in very high concentration of calcium, sodium, and bicarbonate to some extent. But above them all is sulfate, and this should have a 2-, okay? So sulfate is a mineral that you sometimes, one part of a mineral you sometimes find in water. And the World Health Organization tells you that you should not have more than 250 milligrams per liter. And here you can see in the bath water, it's 891. So according to the World Health Organization, the reason for this is that sulfate goes into your digestive system, but it does not go into your body. Instead, it stays inside your intestines and eventually exits through your rear end. But while it's inside your intestines, water flows from inside your body to inside your intestines to help solvate the sulfate. And as a result, you end up with water in your intestines, and that is diarrhea. Okay, so at this point, actually, I should just, maybe I'll cast some speculation here that maybe the Romans were right. This was having therapeutic properties, right? They drink a glass of this water and things get moving. Who knows? Anyway, let's get to the brewing very, very briefly. Is that my most recent arm of research in coffee has been now actually adding water to coffee and actually brewing something. And I originally and very recently dabbled in constructing a mathematical model which simulated water moving through a bed of coffee that contained big pieces and little pieces, much the same as you saw experimentally. And there's an ongoing problem with this, is because how do you quantify what's good, right? How do you know if the extraction that I predicted or I brewed is actually objectively good? Well, there has been a paradigm in coffee where we make a measurement based on Brix, which works well for wine, because in wine you start out with, let's say, 15% by mass sugar, and after a while it turns into ethanol, and you can measure the change in refractive index over time of the liquid based on the transition from sugar to ethanol, okay? Well, in coffee, we care about two things: extraction yield, which is the mass of coffee that ends up solvated in the cup. So if I use 20 grams of coffee to brew the coffee, and I only get 4 grams of coffee out, 4 out of 20 is 20%. So the 20% extraction yield. And then the total dissolved solids is the concentration. So if I have 4 grams of coffee in 400 milliliters of water, then that's 1%, right? And so hopefully then you can see here that extraction yield versus total dissolved solids tells you sort of a concentration versus maybe something related to flavor. And this is the best we've got at the moment. I'm, an area of active research in my group is trying to figure out how we can improve upon making objective statements about what's in a cup of coffee. The reason this has posed historical problems, without going into too much detail, is that water has a refractive index of 1.333 at room temperature. But the refractive index is proportional to the density of water, where something like ethyl acetate creates, networks of water like this. Something like sugar in water causes water to interact more strongly with it, so maybe it's locally more dense. And then something like sodium chloride in water causes water to very strongly interact with it, being even more dense. And so we approach a problem where actually if I dissolve 5% by mass of ethyl acetate, I get the same refractive index difference as if I dissolved 1% by mass of salt. And so this is a big deal, right? Because if I'm trying to use refractive index to tell me whether the cup is going to taste of something and I measure 5%, I have no idea whether it's 5% salty water or 5% ethyl acetate water. Okay, in this example, both of these are going to taste bad, but you get the point, is that the refractive index measurement is probably not ideal. And then in addition, that measurement is very temperature sensitive, okay? Furthermore, and perhaps one of the final slides of this talk, is that temperature really makes a difference in not only the total amount that you can extract, but also the relative ratios of what gets extracted. So if I use any temperature water, I'm going to basically extract all the caffeic acid available over time, right? So I go brew for a long time. And at some point for this particular coffee, I was able to extract about 4 milligrams of caffeic acid per gram of coffee that I used. But if I use cold water and I measure then the concentration of caffeine and project this to infinity, then I can get at about 20 degrees Celsius, I can get about 9 milligrams of caffeine per gram of coffee. If I brew at 90 degrees, I get almost double that. I get 15 milligrams of caffeine per gram of coffee used. And so here's a problem, because if I make a refractive index measurement, I have no idea whether I've got, high caffeic acid relative to caffeine, or whether I've got really high caffeine relative to the concentration of caffeic acid. And moreover, this means that the flavor differences between cold brew and hot brew are going to be significant. And we can talk more about that perhaps in question time. But since we're only measuring one refractive index, I can fit my model with one diffusional coefficient and one rate constant. And all these are is telling me how fast does coffee stuff leave the coffee particle and end up in my cup, okay? And with that, my model is able to predict extractions of coffees and plot that versus something real, like the grind setting, and tell you that if you use high, a high amount of coffee, so if you're trying to brew a really concentrated cup of coffee, and you use a finite amount of water, you're not going to be able to extract as much as you thought. Yet if you use less coffee, you're probably going to end up with lower concentration, but you've extracted more from it. So typically then less coffee ends up tasting more over extracted, in other words, more bitter and unpleasant. And high doses end up tasting very concentrated, but also highly acidic because you've extracted only the front end of that coffee. Now there's a whole bunch of parameters that go into this. We can talk more about it afterwards. But I simply want to put that in our most recent paper, this model is doing a very good job of predicting reality. So with that, I want to leave you with 3 take-home messages. First of all, that water is extremely, extremely important for determining coffee quality, and particularly bicarbonate. So if you have hard water, hard infers high levels of calcium typically and high levels of bicarbonate, then it's going to wipe out acid. And that means the coffee is going to typically be perceived as lower scoring and less pleasant to most people. If you like it, that's fine. Additionally, water also is very important in the industry because we use water to determine the quality of the coffee on the cupping table. So therefore, water is all along the supply chain. So this is an area that doesn't only affect us in the consuming country, but has tremendous impact in the producing country as well. Next, I want to point to optimizing the grinder, is that basically these grinders produce almost all tiny little particulates. And so if you were going to spend any amount of money on a piece of equipment to rapidly improve your coffee process, first and foremost, I'd say pay attention to what's in the water. But if you can't change that, you can't change that. But you can change the grinder. And now a grinder that produces a more homogeneous particle size is going to give rise to more reproducible and predictable extraction. And so we can talk more about the optimizing grinders. Perhaps you can send me an email if you're looking for a recommendation. And then finally, I actually want to encourage you all to remember to taste your coffee. Because I'm not preaching to you that there is one flavor profile that is better than the other, or that you should even pay any attention to the water or the grinder whatsoever, but rather just be paying attention to whether you are able to reproducibly achieve the flavors that you seem to enjoy in coffee. If you are able to do that, then you're doing you're basically performing scientific experiments. You're adhering to the scientific method, and there's then everything I've said is merely an incremental advance on your already well-refined process. So with that, I want to thank a few people, and then I'll happily take questions. The work was made possible by baristas and roasters that have donated a tremendous amount of time, intellectual input to teach me coffee, as well as their wares. I received tremendous amounts of coffee and equipment and expertise from these fine people. The equipment manufacturers have also donated equipment because it turns out that the people who sell the equipment also have an interest in coffee, and we just all want to do good science together. And then finally, there's other academics like myself that work on these sorts of projects, and we all simply share a passion for this. And so that's really where our time and effort comes from. But it's certainly, as I remind you, it's not why I'm employed at Oregon, but it's certainly a benefit for me being here. So with that, I'll say thank you once again for the invitation to speak. And I'm sorry that we couldn't do it in person, and I'll happily take any questions.
Thank you so much, Chris. That was excellent. So far, we only have one question coming in, so I just want to remind people watching, regardless of whether you're on Zoom or Facebook, that you can go ahead and add your questions to the chat features on those 2 platforms. I'm going to go ahead and kick us off with a question that I had, which is, do you have a favorite place to get coffee here in town?
Yeah, so I'm speaking to you today from College Hill, where I live in Eugene, and there are several good high quality coffee roasters that you could visit and experience a naturally processed or washed coffee. Um, I'm going to name a couple, but if I forget one, then it's not a statement about their quality. Okay, so I've worked extensively with tailored coffee roasters here, which are roasting out of Fifth Street, Fifth Street Market area. But on the same area, there's also Farmers Union, which was previously known as what was it called? Slightly Coffee. But then we needn't forget about Equiano coffee roasters out in the Wit. And then finally, there's also, there's two more. There's Coffee Plant Roasters, which is out on West 11th. And of course, probably the most old school and one of the grandfathers of the industry is Wandering Goat, which is also on the Wit. And they really specialize in naturally processed coffees. So if you're interested in trying one of those and you've never had it, definitely go check that out. For me, I don't have a favorite. Whenever someone makes me a coffee, that's about as good as it gets. Just because I didn't do it, someone else did it. So there's passion in that.
And somehow things always taste better when someone makes it for you, I feel like.
Oh, absolutely. Absolutely.
So one of the attendees is asking, at what quality level do you place Jamaican Blue Mountain coffee?
Hey, that's a really interesting question, because Jamaican Blue Mountain coffee was historically one of the higher scoring coffees back when the coffee industry was sort of undergoing this paradigm shift towards favoring more acidic coffees with nuanced flavors. But it was also one of those coffees that had a brand name, right? It was like Kona Coffee, Blue Mountain Coffee. These were brand names. And as a result, the demand went up. And typically when demand goes up and you're on an island that is producing a crop, you have to, you see typically a decline in quality as you scale up. And so actually there are examples of high quality Blue Mountain coffee these days, certainly, but you actually don't find it as nearly as often as you would find, for example, high quality coffee from Guatemala, Nicaragua, Ethiopia, and so forth. And so it's more of a statement about the score sheet as well, is that they're not nearly as acidic as some of these East African coffees. And since the score sheet is structured to value that simply means they just score lower on that. And so you don't run into them as much. Certainly in the arm of the industry that I work with, you don't run into them as much. But it's definitely not a statement about quality. In fact, if you like them, then there's a good chance you probably like pulped natural Brazil coffee as well, which is, they're fabulous. So.
All right. We have one other question that has come in. What can we do to optimize the water in our area to create the ideal cup of coffee?
Yeah, this is a really tricky question, because you don't really know without doing a little bit of work what's in your water in the first place. And so the first thing you can do is look up on the website that feeds your municipal water supply, and they'll give you a mineral composition for what's coming generally out of their reservoirs. But that does not mean that that's what's entering your home. Okay, so this is very difficult, because when I was living in Boston, I lived in Cambridge across the river, and then I moved to Boston for the second year I was there. And the cafe I went to, same everything. One was in Boston, one in Cambridge, and the coffees were completely different, and because the water sources were completely different. So without knowing where you are, I can't tell you exactly what's in your water, but I can tell you that you can obtain that information very, very cheaply by going online and finding a little titration kit that will basically tell you the hardness of your water and the carbonate hardness of your water. So general hardness and carbonate hardness, or temporary hardness, as sometimes it's referred to. And so I'm seeing here that's the Mackenzie River water. Yeah, so everywhere around here is extremely soft. In fact, I heard an anecdote once that the Mackenzie River is so soft that the state actually adds minerals to it so that we don't have problems with algal blooms and other issues, growing in the water. So the Mackenzie water is really soft, and so typically you find that if you're feeding straight out of the Leeburg Dam area, that sort of area, that you're going to have really acidic cups of coffee. But like I said, get a titration kit that costs you $10 or something. And you'll be able to do the assessment yourself. You'll also be doing a titration, which is cool. And you'll be able to put a pin on the graph that I showed you of water chemistry. So then you'll have at least some knowledge as to why you're tasting a certain way in the morning, and then you go camping or something, it tastes a different way.
Perfect. Are there any like the water filtration systems that you can buy just that
Yeah.
you do straight from the tap and keep in your refrigerator or something like that? Do any of those improve the water around here or hurt the water for coffee?
So there's two general types of filters that you can commercially find. One is an activated charcoal filter that typically is, basically it's made from roasted coconut husks, and they're then turned into the black material that is used to filter water through it. The reason it works or what it does rather, is the coconut husks absorb organic molecules that have shown up in the water, so that they may impart a negative smell, taste, or color to the water before brewing the coffee. Now, those sorts of activated charcoal, those types of filters, they won't do anything to the mineral content. So if you have bicarbonate in your water, that charcoal won't do anything. Now, Brita filters, something you might come across occasionally, actually have a mixture of activated charcoal and this other type of filtration system, which is called ion exchange resin. And the ion exchange resin is basically a piece of a polystyrene bead that on the outside of the bead, it is able to substitute, for example, sodium into the water and then capture the calcium. And it can do other things as well. And so there's a variety of different types of ion exchange resins. Some of them go after bicarbonate, some of them go after calcium. And without looking at an exact product, it's very difficult to tell you what one would do what. But generally speaking, activated charcoal almost always helps out coffee brewing water in the sense that it makes water not have a flavor itself before you brew coffee. And then the ion exchange resin, that really does need a titration prior to the making that statement, because if there's nothing in your water, then passing over an ion exchange resin doesn't do anything at all.
So we've had a few more come in, which is great. Someone is asking, they say, I recently heard a lecture about plant genetics where the teacher said attempts were being made to breed coffee without caffeine. Does the absence of caffeine in coffee affect the aroma and or flavor?
Yes. Oh, that is let me see. I can click answer live. Here we are. Absolutely, Rebecca, this is a fabulous question. So caffeine, as I mentioned earlier, kills bugs, but it is also the molecule that we use to teach people how to use the word bitter. So it's an extremely unpleasant compound to humans, despite the fact that we actually somehow enjoy it. And so I'll get to the plant genetics part in a second, but to answer the latter question, coffees with the absence of caffeine taste, basically bitterness goes away. The reason that decaf coffees historically, decaffeinated after they were grown, have been bad is because people have been decaffeinating cheap coffee. They take something that scores low on the score sheet, they remove the bitterness, and now that what's left is all this terrible stuff that was not masked by this bitterness. So now it really serves no purpose whatsoever. Okay, so nowadays you can get really high quality decaf, not necessarily genetics like you're talking about, but post genetic decaffeination, and those can be beautiful. But then now you're also talking about plant genetics, and there is World Coffee Research, the people who I mentioned at making the flavor wheel, they are also investing a tremendous amount of money to look at genetic crossbreeding and hybrids of coffee plants that might be able to sustain higher temperatures, droughts. They may very well be looking at coffee plants that don't produce caffeine. But hopefully you might see then that this could be a bit of a problem for keeping the bugs away from the fruit, right? So there's going to be new challenges associated with that. I'm not in genetics, so I can't speak any more than the fact that caffeine tastes bitter. But if they are making coffee without it, that's awesome.
Thank you. So Carl is asking, why do the Ethiopians add salt to their coffee?
This is another interesting question. Ethiopia is one of, if not the oldest coffee consuming cultures in the world. And there, if you ever have an opportunity to observe a coffee ceremony in Ethiopia, it's there's a lot to it, including adding a little bit of salt sometimes, but also roasting it and the whole process. The salt addition is something that I've observed anecdotally, but don't have a good scientific understanding for why adding salt would do anything beyond making the coffee taste ever so slightly more salty. But I know that if people add salt to their coffee, it somehow smooths it out. And I've been thinking about this for a very long time, and it cannot come up with why that might be. And so typically in my experience, when I think about a problem and I can't come up with a chemical solution, it's almost always because it's a perception issue. It's a sensory science difference. And the reason that this might be playing a role is that if you add salt, maybe the salt sort of acts in unison with other flavors that you'd find in coffee, changing the way that we're perceiving them. But honestly, it's merely speculation, because I really, I don't understand why people do this, but I know that they do. I should note it's not only Ethiopians that do this. There was a whole movement of this in the United States in 2015 that seems to have gone away, which is, maybe for better or worse, who knows?
If anyone who's watching has a theory on why the salt might be, feel free to drop it into the chat or follow up afterwards with Chris.
Yeah, please do. Hey, I see Celia's asked something.
Yeah. She is asking if you could talk a little bit more about the 3 types of grinders.
Right. Okay. Yeah, I really did blow through this real fast. Sorry about that. Okay, so let's go through each of the technologies briefly, and then I'll explain to you which one is inferior. Okay, the top is the blade grinder, is the thing that you'll find where you push down on the top, you put the beans inside. There's a little whirly blade that zips around in there, and the more times you push down, the blade keeps spinning around, right? In that grinder, you put the coffee in, and you keep grinding until it's ground to your desire, and then you tip it out again. The next is conical burr. So the conical burr, this outer ring, the bigger ring here, is basically a bezel. And then the little ring that I've shown here is a drill bit. So it's a drill bit sitting inside a bezel like this. And as you pull the drill bit out, you create larger gap at the bottom. So when the coffee goes in, it gets ground up in the drill bit. And then if the drill bit's pulled out, then big pieces can fall through. And if you push the drill bit in deeper, then the pieces have to be smaller to make it out the other side. And so already you can see the difference between the blade grinder and the conical burr grinder is that in the conical burr grinder, when the particles are sufficiently small to exit the grind chamber, they do. Whereas in the blade grinder, there's a chance that they just keep getting broken up further and further and further. And so we've all had the experience with the blade grinder where you put coffee in, you grind it for a while, and somehow there's magically still a whole bean just sitting in there. And you can't, and that will never, ever happen in a conical burr grinder because gravity is pulling the coffee through. Then finally, sort of more industrially relevant in the coffee industry is the flat burr grinder. And what this is one burr stays stationary, the other burr is spinning at relatively high RPM, and the coffee is fed in through the hole in the middle. And then what happens is the coffee gets broken up inside these two plates, and the fine particulates spray out in 360 degrees all the way around the outside. So it's like, it's basically one rotating plate, and the difference, the gap between the two rotating plates is what determines the size of the particles. In both the conical and the flat burr examples, there is an aperture between two pieces of metal, a distance between them, that determines the largest piece that can exit the coffee grind chamber. In the blade grinder, there is no such device, which means that if you want to achieve, let me go to the graph. Oh, I'm sorry. Let me go to the graph here. If you want to achieve a well-defined largest piece, you need to make sure that that largest piece can exit the grinder when it's sufficiently small to exit. And so these plots here are from a burr grinder. They're from actually a flat burr grinder. if you were to look at the same spread from a blade grinder where you push down and you get the, all the way from microscopic dust all the way up to a whole bean, I don't actually know. I mean, I could only speculate as to what this plot would look like, but it would be total chaos. It may just be this really broad, smooth line. And it's really difficult to brew coffee with that, because you're going to have to pack the coffee in somehow into some small space. And if there's big pieces, then water is going to want to, flow around the big piece. And you can hopefully see there's problems here. And so when I mentioned actually at the end of the talk that your grinder matters a lot, now I'm going to go back a whole bunch of slides back to the shapes. The first and most important thing you could do if you're going to spend even just a little money is to invest in a conical burr grinder, right? They start at like $30, and the one I use is, and I would call myself relatively deep in the industry. The one I use is $120, right? So it's not like it broke the bank. I know that's a lot of money for some people, but it's a good investment because it changes your life for the positive. So yeah, if you could stretch the budget to get a conical burr grinder, that would help.
All right. Well, we haven't had any more questions come in, so I just want to leave it with, if you have one final sort of trick or recommendation for people that they can use to make a good cup. We've heard about, at this point, the grinders. Is there like the different sort of drip systems that people can purchase, or how they make their coffee, something like that? Any recommendations that they could take away from this?
Yeah, so I've got yes, it doesn't involve money, which is good. All right, so the first thing that I would recommend is, if you have a kitchen scale, a small scale that measures in grams or ounces, that you should start to weigh out the mass of coffee that you're using, and then also weigh out the mass of water that you're pouring on that coffee. Now, it doesn't matter which brew method we're talking about, right? If you're using a French press or an AeroPress or a pour over or a Mr. Coffee, it makes no difference. And the reason I'm recommending this is because at the very end of the talk, I mentioned that one of the important, I'll go to that real quick actually. One of the important factors in brewing coffee is the relationship between how much coffee you extracted into the cup, which is the mass of solvated coffee, divided by the mass that you used in the first place. Now, if you don't weigh it, you don't know. You have no idea the bottom number, right? Now, you'll never know the top without fancy equipment, but you'll have no idea about the bottom one. And if you don't know the bottom one, and you also don't know how much water you poured in, then you'll never be able to reproducibly brew cups of coffee. So simply put, weighing the cup of coffee that you're brewing, both the water you use and the mass of coffee, is extremely important. That's probably the first and most important thing. And then from there, I mean, sure, there's some tips that I have. Like, for example, my favorite brew method is an AeroPress, which is just a glorified syringe, right? It's a big syringe. I love it because you need to grind fine for an AeroPress, very fine. Let's say, on my grinder, it's, getting close to espresso size, and you only brew it for 1 minute and 15 seconds. And, I use 15 grams of coffee. I brew for 1 minute, 15 seconds. And at the end, I've got a lovely cup of coffee. But what's nice then is that if I want to go fine, I can use a blade grinder too, because they make fine dust as well. So I, that's my tip is, weigh things, and also use an AeroPress if you want to buy something else, but just weigh things, and that'll take you, 80% of the way to excellence. But I see some more.
We have had a couple more people try to sneak some questions in, so we'll go ahead and chat a little bit longer if you don't mind.
Sure, of course.
Phil's asking if you recommend bottled water.
Yeah, hey Phil, that is a heavy question. Okay, so let me go to this picture here. This is right here. What this is the back of a bottle of water that I found in Switzerland when I was there back in December. And you can see this number 153 for bicarbonate. Well, that's a pretty high number, but if you want to go even higher, you can go to Evian, which is 360. Okay. Now, soft water coming out of the tap in Eugene is on the order of 10. Okay. So the difference here is like tectonic. It would, let me see if I got my graph here for you. So I just showed you 150 on the back of that bottle. 150 is so far off to the right of this graph that you won't, I mean, looking for acid in that coffee would be like, a needle in a haystack. You won't find it. Okay. It's not going to happen. So when you ask about bottled water, the answer actually is which bottle of water. And I already encourage you to go and experience a bad bottle of water. So go and buy Evian. It's not, I mean, the water itself is perfectly drinkable, of course, but brewing coffee with it is terrible. And the reason is it wipes out all of the acid. And then if you want to do a fair bottle of water comparison, then you can go buy something much softer like, I don't know, Dasani. That's a soft water. And you boil that up and brew it exactly the same. Remember, you got to weigh everything, right? And if you do that, you'll then see that Dasani puts you over here and it'll taste really sour, and Evian will put you over here and it'll taste really chalky and heavy and quite unpleasant. And somewhere in the middle is ideally where you want to be. And I found Poland Spring, which we don't see much on this coast, but Poland Spring puts you pretty close to the middle point over here. And people also tend to like Crystal Geyser for brewing coffee as well. So those are a couple of examples. In all cases, the mineral composition is reported. If it's not on the bottle, it's online. So you can check that out.
Okay. And then someone is asking if you could talk a little bit more about the pros and cons of freezing or not freezing coffee, and whether it's better to store coffee as full beans or as ground coffee.
Yeah, that is a good question. Okay, so here we are. Okay, so there are some major difficulties with storing coffee in the freezer. The first problem is that the freezer loves to condense water into ice, right? That's what we use it for, basically. If you put roasted coffee near water, it will absorb water because it used to have, some water in it when it was a plant, and then we roasted and drove it all off. So now it's going to be way drier than the atmosphere that it's in. So it's going to absorb water. And that means that if you just put coffee in the freezer, it's going to absorb like all sorts of stuff in there. One of the things you can think about, like, you don't want your coffee beans to smell like fish sticks, so you don't want to, gotta cover them up somehow. Okay, so point one is that you have difficulty with coffee absorbing water and smells and other stuff. Point two is that the whole bean coffee freezes way better than ground coffee. And the reason is that once you ground the coffee up, you've exposed so much surface area, like way more than the whole bean, that now all those lovely molecules you're trying to keep in the coffee can escape. And so in the process of just grinding it and then, putting it in a mason jar or a baggie or something, you've already lost like a tremendous amount of the lovely stuff that we care about, right? And so that's difficult as well. But I'll be honest, I do it. I store ground coffee. If someone gives me ground coffee and I can't get through it, I'm going to put it in an airtight bag in a freezer. And here you see a couple of interesting things. In this slide, you can see these are whole beans, right? And the ones in the test tubes, they're going to be used sooner rather than later. So they weren't stored airtight. Somebody just packaged these up, put a little lid on them, and that was the end of it. And this isn't a cafe, so they're probably going to get through all these vials in one day. These ones in the food safe vacuum sealers, the vacuum sealing process removes all the water and all the gas that is in the immediate area. It doesn't degas all the coffee though, right? So you just pull vacuum for a short moment and then you seal it up. This is obviously a problem in the sense that we're generating plastic waste, and we're obviously looking at ways that we could reduce this. But if you're going to store whole bean coffee and you really care about the coffee, this is worthwhile, right? Because you're now preventing anything from going into the coffee. You're also preventing anything from leaving the coffee. And so if you store it like this in the freezer, it lasts forever. So that was point 2 or 3, depending on which way you want to think of it. And then there's another consideration, right? Is that the issue with storing coffee in the freezer is that you're probably like me, that we open a bag of coffee and we get through it in about a week. Have a couple cups a day, or maybe a cup or two a day, right? And maybe you're slower than that. Maybe it takes you 2 weeks. Well, if you're going in and out of the freezer every time and you open up the coffee, you dose out a little bit of coffee, that process where you open it up to air, all this air that's full of water then goes in and finds cold coffee, and all the air, all the water in the air will condense onto the beans. And so if you do that for 2 weeks, the last cup of coffee you're going to have is going to be pretty unpleasant. after those 2 weeks. And so this idea that you come up with a vessel that you can put into and then remove from the freezer and somehow not expose the coffee to air every single time is a problem that we haven't really solved. One solution was put in the freezer, take it out of the freezer, let it warm back up to room temperature, open the lid, and what. But who's got time for that, right? I mean, we're talking about a cup.
Haven't had your coffee yet.
I mean, we're talking about a cup of coffee here, right? It's like, that's lunchtime by the time that's done. So, so look, there's not really a good solution. The reason we do this in the first place is because more often than not, in my household, right now I've got a washed Ethiopian, I've got a washed Kenyan, and I've got a really unusual Costa Rican natural. And all three of those coffees are lovely, and I don't want them to taste, I'm going to get to them, but I want them to taste good when I get to them. So I put them in the freezer in a sealed vessel, and then I get to them when I can. And then I just go through the bags one by one. And when I pull out the bag, it stays on the counter until I'm done with it. But yeah, there's logistical challenges. If you've got the patience, you could dose it out like this, and that would teach you how to use the scale really well as well, because then you put the exact amount of coffee in each test tube that you wanted. But like everything, that you got to draw a line somewhere.
Well, I think that's it. So thank you again for the talk tonight and for spending your evening with us, especially on today of all days. And thanks everyone for tuning in. I hope that you all enjoyed the talk as much as I did, and we'll see you next month. Thanks again.